PN junction working. In P-type material, the majority positive charge carriers are holes. In N-type material, the majority charge carriers are negatively charged electrons. Normally, holes and electrons are uniformly distributed throughout the volume of P and N-type semiconductors, respectively. Semiconductors of P and N-type are brought together. Electrons and holes migrate across the junction. Then the depletion layer is formed. A potential difference is developed across the depletion layer. The movement of charge carriers across the junction leaves a layer on each side which is depleted of charge carriers. This region is called the depletion region. In the depletion region, equal number of impurity atoms is involved on each side of the junction. The thickness of the depletion region is same on both the sides when the two blocks of material have equal doping densities. However, the thickness of the depletion layer depends on the amount of doping on each side. PN junction diode. When one part of the germanium block is doped with a trivalent impurity and the other part is doped with a pentavalent impurity, a boundary called PN junction is formed between the P-type and N-type portions and a basic diode is formed. A diode is a device that conducts current in only one direction. The PN junction is a feature that allows diodes, certain transistors and other devices to work. The P-type material consists of germanium atoms and trivalent impurity atoms such as boron. The boron atom adds a hole when it bonds with the germanium atoms. Since the number of protons and electrons are equal throughout the material, there is no net charge in the material and so it is neutral. An N-type silicon material consists of germanium atoms and pentavalent impurity atoms such as arsenic. An impurity atom releases an electron when it bonds with 4 silicon atoms. Since there is still an equal number of protons and electrons throughout the material, there is no net charge in the material and so it is neutral. If a piece of intrinsic silicon is doped so that part is N-type and the other part is P-type, a PN junction forms at the boundary between the two regions and a diode is created as shown above. The P region has many holes, majority carriers from the impurity atoms and only a few thermally generated free electrons, minority carriers. The N region has many free electrons, majority carriers from the impurity atoms and only a few thermally generated holes, minority carriers. A semiconductor diode is a PN junction which has connecting leads or terminals on two sides of the junction. Biasing of diode. When P-side anode is connected to the positive terminal of the battery V and negative terminal of the battery is connected to N-side cathode, then the diode is said to be connected in the forward bias. Under forward biased condition, holes are repelled by the positive terminal of the battery. Electrons are repelled by the negative terminal of the battery. As a result, depletion region decreases. Holes in P-side, majority carriers, cross the junction from P region to N region and electrons in N-side, majority carriers, cross the junction from N region to P region. This phenomenon leads the current through the diode. Cut in voltage is a voltage at which the diode starts conduction. Diode in forward bias offers low resistance, acts as a switch in a closed position. When P-side anode is connected to the negative terminal of the battery V and positive terminal of the battery is connected to N-side cathode, then the diode is said to be connected in reverse bias. Under reverse biased condition, Holes in P side move towards negative terminal of the battery and electrons in N side move towards positive terminal of the battery. Hence, the width of the depletion region, which is depleted of the mobile carrier, increases. As a result, no current flows through the diode, but in practice, a very small amount of current flows, such as few microamps. Diode in reverse bias offers high resistance, acts as a switch in an open position. The symbol for a diode is an arrowhead and a bar. The arrowhead indicates the conventional direction of current flow when the diode is forward biased, that is in the direction of holes, or opposite to electron flow.